Okay.
Yeah.
Good afternoon, everyone. Okay, we should start. So first, I will soon release the deadline for your course project, including the project team and topic project. If you choose the casual computation, our TMs will send you an invitation link. Otherwise, you need to specify your project team. You want to do the solo project, or you want to form a partner. And then our due for the midterm project is scheduled right before the spring break, because I don't want to bother you during the spring break. So I hope before the spring break we'll have like intermediate report on that. So any questions?
When is the deadline for proposal?
For proposal?
Yeah.
We'll release very soon. Probably it's in 2 weeks.
2 weeks.
Yeah. That should be in 2 weeks. And then, like by the end of January, I hope hopefully you will have your general idea of doing whatever you want for the project. And then you have like, because our spring break will begin on March 7th, if I'm not wrong. So you'll have like over 1 month to do to get some like intermediate results. I think that should be sufficient. Any other questions? Okay, so let us continue with decision trees. So in the last lecture, we introduced the classical decision tree learning algorithm called ID3, right? So ID3 is essentially a greedy heuristic algorithm. Like every time we choose the best feature that splits the current data subset, and then use that feature to split the trees. So the heuristic is that I'm gonna choose the feature that after it's split, the data set is as pure as possible. Because our goal is that I want to find out the structure of the tree to be as small as possible. Right? That is a so-called Occam's reasons principle. Right? I want a model to be as small as possible to explain or summarize the data. So if we choose this kind of principle, we want to develop an efficient algorithm to find out such a tree. So the global search, although it can guarantee the unique smallest tree among all possible trees, right? But it will be too computationally costly. It's going to be hard. That's why we choose to use a more practical algorithm, that's greedy algorithm. Right? Greedy algorithm, although does not guarantee the global optimum, but it usually results in a very small tree. It's close to the global optimum and in a very with a very fast speed. Right? That's the key idea. Right? So today, we're based upon ID3 algorithm. We'll talk about some extensions about that and how do we choose different measurements to split the data sets, and how do we handle missing and missing examples, right? So here are the topics we're gonna cover today, right? So first, we'll talk about a few variants of ID3 algorithm. So the variants lie in how you measure the increase of purity after you use a feature to split data set. So in our last lecture, we used the classical measurement. It's called information gain, right? Which is based on entropy, right? But obviously, you can measure the purity of your data set based on other metrics, right? So as long as it's reasonable. And then you can define a similar kind of way to compute the improvement of purity after splitting the data set, right? So we'll introduce two simple but also popular purity measurement. And then we'll talk about, in practice, how do we handle examples with missing feature values. So actually, the practical applications are always dirty and noisy. So in the future, if you have a chance to do some real-world applications of machine learning, you will find like the data sets are really, really bad. You'll see a lot of examples without labels, without one or two, or even like several feature values, right? But you still want to pre-process them and then throw them into some machine learning algorithm. So how do we handle those kind of incomplete examples of when we construct the same tree? Right? We'll talk about several strategies. And then we'll talk about non-binary features. So what if you have like a discrete feature that can take 1,000 values, right? That means if you use that feature to split your data set, you're gonna add 1,000 branches of tree. That's too wide, right? The tree is too large. So can we further simplify the tree, right? By removing so many branches. So we're gonna talk about how to do that. And finally, we'll introduce a very important concept called overfitting. Right? We briefly mentioned it before, but I haven't given you a concrete case about that. So we'll see what is overfitting and why overfitting can hurt the generalization performance. So first, we'll talk about the variance of distributed learning based on ID3, right? So let's take a brief review of ID3, right? ID3 is a recursive algorithm. Like recursively partition the data sets and add more nodes in your tree and branches in your tree until you reach the leaf nodes, right? So we have three input variables for the ID3 algorithm. First, S are these current set of examples. Right? Remember, each tree node represents a subset of training examples. Right? So if you recursively call your ID3 algorithm, S may just represent the current subset of examples, which corresponds to an intermediate node in the tree, right? Of course, if you call ID3 from scratch, then S will be the entire data set. Then the label is the target attribute you want to predict, right? Attributes is a set of features from which we're going to select the best feature to split the data and to create new branches, right? So this is algorithm steps for ID3. So first, as we mentioned, like ID3 is a recursive algorithm. We need to first specify the stopping criteria or the base conditions, right? So when should we stop calling ID3 to create new branches and nodes, right? When all the examples have the same label, right? So if your current set of training examples have the unique label, it's not necessary for us to further split the data set, right? So we should stop. And also another subtle situation is that if you don't have any attribute to split the data set, you have to stop. Even you still have like mixed labels, right? In that case, you're gonna choose the majority label in your current set as your label for your leaf node. So this is just the boundary case, right? The base case. Other than that, we can still partition the data sets, so create new tree nodes and branches, right? How can we do that? First, to create a root node for the tree. The tree could be the current tree, or it could be the subtree, right? And then we go through each attribute in a current set of attributes. We find out the attribute that best splits the current set S, right? So as we mentioned before, right, best splits that means that when I use this feature to split data set, the split data sets are purer than using any other feature to split the data set, right? And then once we identify the best feature A, we're going to look into all the possible value that A can take. Right? For each value, we add a new tree branch where the test condition is that this feature A takes value B, right? And then from S, we can take out all the subset examples where the feature A takes value B, right? We denote it by SV. Right? And here is the subtle corner case should worth your attention. So if SV is empty, that means for the current set of examples, no example whose feature value A takes this specific value A. That means SV is empty, right? In that case, we still need to add leaf node. If we do not add leaf node, what is the consequence?
Yeah, cases where you'll have inputted data that your algorithm just doesn't spit anything out for. It doesn't have an output for certain inputs.
Yes. Yes. Right.
The triangle that we have.
Yes, that's the example we mentioned several times, right? So if you do not add a leaf node here, you will have a chance to meet a specific test example where you don't have any paths going from the root to the leaf node, right? So suppose like your test case pass the test conditions and reach the current node, right? And then you look at the test condition that A equals to B, and embarrassingly you found, okay, there's no branches on there. That means you don't have any label on there. That's embarrassing, right? That's not allowed, actually. Whenever you create the classifier or predictor, you should guarantee that for any test instance, you provide some prediction. You cannot say, okay, I refuse to predict. So in this case, I'm going to add a leaf node, and then I choose the most common label in S as my prediction on that leaf node. The reason is to generalize as test time. Otherwise, if SV is not empty, we can still recursively partition the subset SV, right? How can we do that? We just call ID3 again, right? That's the ID3 call itself, right? So now the subset of examples is SV. And to partition SV, we cannot use the previously selected feature A anymore, right? Because all the feature values in SV will take the same value of A. So we need to exclude it, and label is the same label, and we call it again. So now we can say, okay, recursively call itself and expand trees and create new nodes and branches until all the stopping criteria are met. Means that you reach all the leaf nodes. You finish tree construction. So I hope everyone feels comfortable about this algorithm. Everyone's good? Okay, great. So once we are clear about this algorithm's procedure, right, the remaining thing is to figure out a way to find out the best feature, right? That means how do we select the feature that best improves the purity of the data set splitting, right? So we use a measurement called information gain, right? So what is information gain? So it's based on a concept from information theory, namely entropy. Entropy measures the uncertainty of the labels of your example in your data set. So if all of your examples have the same label, you're completely sure about the label of examples. That means you have zero uncertainty. But on the other side, you can say, okay, your data set is purist, right? Because all the labels are the same. It's a purist. Right? But if your examples, say, like have a half positive, half negative examples, you're most unsure about the labels in your data set, right? Half chance to be positive, half chance to be negative. So your uncertainty reaches maximum. It is equivalent to say your purity is worst, right? You have half positive and half negative is worst, right? So you can see entropy is a natural representation of the purity of the data set. And the larger the entropy, the worse the purity, or the smaller purity. That means, okay, the decrease of entropy indicates the increase of purity, right? That's how the information gain is defined. We first compute to measure how the purity of the data sets are improved after you use a specific feature A to split data set. I just measure the difference of the entropy before the splitting and after splitting. Right? So before the splitting, I calculate the entropy of the entire data set S. But after the splitting, the data set is split into several subsets, right? So I can compute the entropy of each subset, and then compute expected entropy. Right? So the expectation is computed by weight each entropy according to the size of the training data. We mentioned why it is rational to weigh the entropy of each subset according to their size. Suppose we have 100 examples. We have two subsets, right? One contains 100 examples, the other contains one example. So the smaller examples definitely has the best purity, right? Because it only has one example, one label, right? But it's much less important than the purity of the 100 examples subset, right? So we need to account for such difference according to the size of each subset, right? That's why we should weight the entropy of each subset and then take the expectation and take the average. Then we use information gain to rank all the features, right? And choose the feature with the highest information gain to split the data set and create nodes and branches. Is everyone comfortable? No one feel confusing, right? I'm just repeating the words I said in the last lecture. Okay, great. So now we see that information gain is based on entropy, right? Entropy is natural representation of the purity of the data set, although it is originally defined to represent uncertainty, but uncertainty is a reflection of purity, right? But someone may ask, okay, is there any other metric to quantify the purity, right, other than entropy? The answer is yes, right? So, for example, we can use the so-called majority error to measure the entropy of your labeled data set. How can we do that, right? So let's see the definition of majority error. Suppose the tree was not growing below this node, and I chose the majority label to make a prediction. The majority error is defined the error of using majority label for the prediction. For example, at some node, I have 20 examples in total, from which 15 are positive and 5 are negative. So what is majority error? According to the definition, majority error is the error that use the majority label to make prediction. Right? So what is majority label? Positive, right? If I predict all the 20 examples to be positive, what is the error? 5 over 20, right? Because obviously those 5 negative examples are all incorrectly predicted, right? So the majority error will be 5 over 20, which is 1 over 4, right? This is how we define majority error. Now I want to ask a question: how does majority error reflect the purity of your data set?
The lesser the majority error, the fewer would be
Pure, right?
better than pure.
Yeah, exactly, right? So it's very intuitive. Like, let us consider like extreme cases, right? Like suppose all of your 20 examples are positive. what is the majority error? 0, right? I mean, smallest majority error corresponds to highest purity. But what if my examples are half positive, half negative? What is majority error? Half, right? So actually, we can show that the majority error for two labels cannot exceed half. Why? Yeah, of course. If you have like more negative than positive examples, your majority label will become negative label, right? And you still get like less than half majority error. So now we can say on the other extreme case, the majority which is the largest, which indicates the worst purity, right? So like entropy, this is very similar behavior as entropy, right? So the larger the entropy, the worse the purity. The smaller entropy, the larger or the better the purity, right? So similar kind of arguments apply to majority error, right? The larger majority error, that means the more examples, the more labels mixed, then the worse the purity, right? And vice versa. Then we can use majority error to define a gain, right? We can call it a majority gain, right? So the decrease of the majority error indicates the increase of purity. So just to follow the definition of information gain, we just replace the entropy by the majority error. Any question? Is everybody comfortable? Okay. And again, we need to take into account the sizes of each split subset, right? So the same formula as information gain. The only difference is that I'm gonna replace the entropy by the majority error. And then we can rank all the features according to their majority gain and find the best one, find the largest one, and to split data set and create triangles and branches. Any question? Okay. So this is the first variant, right? Let us talk about another variant. It's called the Genie Index. Genie Index is also a very widely used way to rank the features in ID3 algorithmic framework. So what's the definition of Genie Index? Suppose we have two labels in our data set. So the Genie Index is defined as 1 subtracted by p minus squared plus p plus squared. So p plus and p minus are proportion of positive and negative labels respectively. We defined them before. Right? And in general, suppose you have k labels in your data set, then the Genie Index is defined as 1 subtracted by the sum of square of each proportion of each label. So pk squared. Right? So now I want to ask, how does Genie Index reflect the purity of the data set? Any comment? Or it's too easy? Again, we can consider like two extreme cases, right? So let us suppose our examples are purist, right? Meaning that they share the same label. Right? So what is Genie Index? 0. 0, right? Because either we have all examples could be positive or negative. That means p plus is 1 or p negative is 1, right? Then the Genie Index is 0, right? And the Genie Index reaches the minimum value. The minimum Genie Index indicates the largest purity. And on the other case, on the other side, right? Suppose my training examples, my data set are maximum mixed half of them are positive, half of them are negative. What is Genie Index? Half, right? And actually, you can show that half is the largest Genie Index for two label cases. That means the largest Genie Index indicates the worst purity, right? So intuitively, you can consider like the smaller the Genie Index. That means okay, some kind of some label is kind of much larger than the remaining labels, right? So say either P positive is quite large or P negative is quite large. Then one subtracted one by their sum could be smaller, right? But some labels are much larger than the other labels, means that your data set is pure. On the contrary, if the distribution of different labels become closer and closer, that means each P plus, P minus is kind of approaching to like half. Then your Genie Index is larger and larger because their square sum is kind of smaller, right? So that means okay, larger Genie Index implies worse purity, right? Instead, the smaller the Genie Index, the better the purity. In the best case, then your Genie Index reaches 1, all of the examples share the same label, then the purity becomes the best, right? So again, this is similar to entropy or majority error, right? So the larger the Genie Index, the worse the purity. That means the decrease of the Genie Index indicates the increase of purity. So now we can define another gain. We can define another gain based on Genie Index, right? First, we're going to compute the Genie Index of entire data set S, right? Then we use some particular attribute A to split data set. We compute the Genie Index of each subset, and then compute their weighted average.
So even though these all use like different measurements for information gain, like usually in most cases they're all gonna choose like the same feature, right? To split the node on. No, like in most cases, like on average, they'll all choose like the same feature.
It's not necessary because they have a. So you can say like qualitatively, right? It's not quantitatively. Qualitatively, they all have like kind of association between different metrics and purity, but how they change, how they vary, are different. So usually, if you use information gain, which is based on entropy to select features, you favor those features with more distinct values. Like one feature has 3 and one feature has 2. If both of them can separate the data set well, then the feature who has 3 distinct values is more likely to be chosen by information gain. And instead, if you use Genie Index, then the feature has 2 distinct values, is more likely to be chosen. So the behavior is different.
And there's no, I'm assuming people have done a lot of tests and like made a lot of trees with these like specific ID3 things. There's no one that's better than the other. Is it just dependent on what data you're trying to organize?
Yeah, exactly. It depends on applications. You have like a bunch of choices of the gains based on different metrics that you can use. Entropy, there is another common use called the entropy ratio. It's C4.5 is more commonly used. And Genie Index is a very popular choice. And the majority error is actually less used than those gains.
So let's say you have like the same data, you make 2 different trees, one using just entropy, and the other using like majority gain. Is there like an exact relationship between those 2 trees in terms of their similarity? Like, is there like an equation that can say exactly how similar they are, or it's totally random?
I would guess it's not totally random, but if you want to quantify the exact relationship between them, it's not that easy. You need to base the relationship between the definition of the Genie Index and the definition of the entropy, right? So how they compute them, you need to look into the relationship about different ways to compute the purity, right? And based on that, you might derive some kind of conclusion, but usually it's not trivial. And as to which one is better, right? There is no exact answer. No one can guarantee that Genie Index is always better than information gain or majority error. It really depends on the applications.
So, for example, you could not convert a tree using one like entropy to a tree using majority error without rebuilding the whole tree from scratch. That's really what I was wondering. Could you convert one tree to the other just using like a closed form equation, or do you have to rebuild another tree from scratch so you compare them?
I don't think you can. I mean, once you got the tree, right, you don't have any information from the data set. You don't have the tree structures. Then the information necessary for you to split data with another metric is lost. It's hard to, yeah, unless like if you restore all the, if you restore the distribution of the labels in each tree nodes, yeah, it's possible. Any other question? Okay. So here's one simple practice, right? So suppose our 20 examples, like 15 are positive, 5 are negative. How do we compute the Genie Index?
It's better to use.
What?
Which of them is better to use to get information gain? Presents 3 methods: entropy, majority error, and Genie Index. Which of them is better to use for generating the tree decision tree?
Yeah, I offer you several choices. And in the practical applications, which one do you like to choose? Depends on applications. For example, if you want your decision tree to have the best predictive performance on some particular application, right, you can test each of those metrics. Right? If you use information gain and your cross-validation shows that your performance, the prediction accuracy is 95, right? And if you use Genie Index, shows that 97, well, I'm going to choose Genie Index. Okay. Okay, so suppose we have 15 positive and 5 negative examples, right? How can we compute Genie Index? According to the definition, the positive ratio is 5, negative ratio is 5 or 20, and positive ratio is 15 or 20, right? You just subtract 1 by their square sum, you end up with 3 over 8. Right? So, for 1, you're required to manually compute the Genie Index for those features, and based on that, to select features to manually create a set of decision trees. So hopefully you can practice those computation. Right? You have a sense on that. So now I have finished the discussion about variance of the decision tree learning. So that's mainly based on how you define purity, and even the way to compute the gains are the same, but the difference only lies in how you measure the purity. So now let us talk about the second topic, right? So missing feature values. So in practice, you will see that many training examples have missing feature values. The very first step before you throw all the data into some machine learning algorithms like deep neural nets, you have to address this headache. Today we're going to talk about how we address this before we construct our decision trees. So we still use the previous supervised learning task we discussed. Suppose we want to construct a decision tree to predict whether I'm going to play tennis according to the weather condition. Right? So previously we created a decision tree with 14 complete examples, right? But now suppose I received a 15th example, right? Which is negative example. Means that at that day I refuse to play tennis, right? But I don't know the outlook of that day. So although the outlook feature is missing, I still view this as a valuable training example I want to incorporate it into my decision tree learning. How do you address this problem?
You could assume that the unknown will fall into the category of the majority element in that, say for Outlook, since all the others are sunny, you could probably assume that it's also sunny for that one instance.
Yes, yeah, that's a great answer, right? So this is the very first, this is a straightforward and very useful strategy to do that. Right? We need to complete the missing feature value. Right? So the first strategy, probably the most common used way, is just to complete the missing feature with the most common value that appear in the training set, right?
When you're recurring, can you instead include that example in both recurrences for different categories so that you don't assume anything?
Yeah, that's a very good question. I will discuss this strategy later. Right. So let us first talk about the straightforward solution. Right. So just to look at, okay, all of the 14 examples, I know the most common value for outlook is say overcast. Then I just assume the outlook value in this example is just overcast. Then I just throw this example as a normal example into decision training the construct tree, right? This is the first strategy, right? So if you want to do a more refined way, we might need to care about the label of that incomplete example, right? As we mentioned, this new example is a negative example. Right? So I might need to take a look at all the negative examples in the training set and look into the most common value of outlook in the negative examples. It might be overcast as well, or it might be other value like sunny. Then I just complete it with sunny. The second approach, right? So both approaches try to find out some most commonly used feature value and use that value to complete the missing feature value. Right? So what's the effect of this approach?
Aren't you kind of like reinforcing that bias may already be there?
Yes, exactly right. So actually, your argument is kind of similar to him, right? Like we know that this feature value is missing, right? But outlook has 3 distinct feature values, like rain, sunny, and overcast, right? So there's still a chance that outlook takes the other 2 values, right? Although the chances for taking different feature values might be different, right? So why not we consider them all rather than focus on one? So this motivates a third strategy. It's called fractional concept. So what is fractional concept? We can take a look at the distribution of the attribute values outlook in the remaining 14 complete examples, right? So we see that, okay, 5 out of 14 examples are sunny, 4 over 14 examples are overcast, and 5 over 14 are rainy. So according to this distribution and the proportion of each distinct value, we can split the incomplete example into 3 fractional examples. This is one incomplete example, right? And then we'll just split it into 3 examples where each example takes a different feature value according to the ratio, right? So we assume that, okay, I just split this one example into a 5 over 14 sunny example, and a 4 over 14 overcast example, and 5 over 14 rain example. So now I have 3 fractional examples. Fractional but complete examples. Now just throw the 3 fractional examples into the previous data set to construct a tree. That's the idea. So how does this fractional example change our computation? Exactly does not change, but you should get used to fractional counts in the size and in the probability. Let us take a look at a concrete example, right? So this is our original 14 training example. Each training example is complete, no missing feature values, right? So suppose I want to test the information gain or majority gain or whatever gain when we use all of the split the data set. So if I use all of the split data set, I got like 3 subsets, right? The Sunny subset has 5 examples where 2 are positive, 3 negative. And the Overcast examples consist of all 4 positive examples. And the Rain examples are 5 and 3 positive, 2 negative. Right? So now, if I add one more incomplete example where the outlook is missing, we use our strategy to split this incomplete example into 3 fractional examples. That means, okay, in addition to these 14 complete examples, I have 3 more examples. Right? Each example takes a different outlook value, Sunny, Overcast, Rain, and also their count. They have different fractional counts, right? So now I just add 3 examples into the 3 piles and compute the entropy and information gain. Like, how can we do that? So first, we're aware of that all the 3 fractional examples are negative examples. Why?
Because the label was negative.
Yeah, because the original incomplete example is negative, right? You split them into 3 negative examples. And then for this fractional Sunny example, we'll put it here, right? So the Sunny example has 2 positive and 3 negative, right? But now I add one more 5/15 negative example. So now we have 2 positive still, right? But 3 plus 5/14 negative example. So now you can see the counts for positive and negative are no longer integers, right? It's some kind of real values. And the size of data are not integers as well. They are 5 plus 5/14. So similarly, for Overcast example, we should add this fractional example, right? For 14, right? So this is a negative example. That means we have we now have like 4 positive and 4/14 negative example, right? And similarly, for the Rain example, we'll have 5/14 fractional Rain example, which is negative. So originally it's 3 positive and 2 negative. Now we have 5/14 more negative example. So this is a new proportion for the positive and negative examples. But in total, how many positive and negative examples do we have? We only have one more extra negative example, right? Because realistically we only have 1 negative example, the feature value is missing. So it's 5, 6, right? Then how do we compute the entropy for each subset? Right? The same thing, right? So we have like 2 positive examples and 3 plus 5/14 negative examples. So the P plus is 2 over 5 or 5 plus 5/14, right? And P negative is 3 plus 5/14 over the entire real value count. Now, real value count of the examples, right? So I have a P plus and P negative. If you want to use the information gain, you can calculate the entropy following the formula, right? And what is the majority error? Any idea? How do we compute the majority error?
Ratio of misclassified ones over.
Yeah. So it's actually, you just pick up the smaller value between P plus and P minus, right? So it should be P plus, right? Because obviously, negative example takes the majority, right? Although the negative number is kind of continuous, but it's still bigger than the positive number, right? So if I use negative example to predict all the examples, including this fractional one, these 2 positive examples are misclassified. So the majority error is just 2 over the total size, right? So which is P plus. So you can see the same thing, right? The computation is totally the same, except that you should get used to fractional examples, the fractional counts. Any questions so far? Yeah, this is a very robust way. It's actually, in practice, it's more favored than using most common values to complete the missing features. But implementation of it is a bit more complex than the most commonly valued method. Right? So also one thing you should be careful is that once you compute the entropy for each subset, right, you need to compute the expectation of entropy over all the subsets. And according to our definition, we need to weight each entropy according to the size of the training set, size of each subset, right? So remember, the size of each subset now is not an integer, right? It is some continuous value. So you should take into account as well. So I'll give you some subtle. I want to mention the subtle detail because in homework 1, which is released today, you need to use a fractional counts to complete missing feature values and say what kind of trees you generate using ID3. Okay. Yeah. Question how to compute the majority error, as we just mentioned, right? And of course, as well as once we have P plus, P minus, we directly compute the Genie index as well, right? One subtracted by P plus squared, subtracted by P minus squared. So we talk about during the training time, if I happen to see an incomplete examples, how can we do that, right? But now, what about during the test time? I have a test instance which has some missing feature value. How can we do that? Suppose my tree has already been constructed, right? And now I give you a test example. I tell you that that day I don't know whether it's overcast or raining or sun. How do I give a reasonable prediction?
Choose different possible values as the missing.
Yeah, that's one strategy, right? But starting from the most straightforward method, we can still first complete the missing feature value using the most common value of the attribute in the training data, but the second strategy is not feasible because we do not know the label of the test example, right? You have something to ask?
Oh no, I was going to say for your test, could you split into 3, get 3 different predictions, and recombine them, giving them their weights and score 1?
Yes, exactly. Right. That's something I'm going to discuss right now. But again, the most straightforward way is that you complete the missing feature value in a test example with the most common value of that feature in the training set. Right? This is the most straightforward way. Right? But of course, we want a smarter way to do that. So we want to use fractional counts again. Right? How can we do that? Right? Again, we split the incomplete test example into several fractional test examples, where each test example, the feature takes a distinct value. Right? Then I can have multiple predictions, right? Now how can we combine those different predictions? We can do a majority vote, right? So I have split the examples into 3 fractional of 5 fractional examples, right? So each fractional example has different fractional count. And then each example has different label, right? And then I just weight each label, each prediction according to the fractional count, and combine them together to pick up the majority voted prediction. Does it make sense? Right? Let us look at a concrete example. Right? So suppose right now I have a this incomplete example becomes my test example. I do not know the all feature. Following the strategy of the fractional counts, I can split it into 3 fractional examples. Right? So fraction is obtained by calculating the proportion of each distinct feature value in the training set. So I have like 5 over 14 Sunny test example, 4 over 14 overcast test example, and 5 over 14 rain test example. Then I just threw the 3 examples into my decision tree, my fancy tree. Then I end up 3 predictions, right? So for the Sunny test example, I predict that I'm gonna play tennis outside. For the overcast, I choose to stay. And for the rainy example, oh, that's kind of weird. But let's just assume, okay, I predict I still going outside to play tennis. Right? And now how can I combine the 3 predictions into one?
So weighted average.
Yeah, weighted average. Right? We call it majority vote, right? So we have 2 positive predictions. The first prediction is weighted by this fractional count, 5 over 14, and second is weighted by this another fractional count, which is also 5 over 14, right? So we'll have the total weight for this positive prediction to be 10 over 14. I have only one negative prediction whose weight is 4 over 14, right? So now we have 2 different weights, right? So we choose the one with the larger weights. So finally, I'll predict the label to be positive.
What about if they're perfectly equal?
What?
If the weights, like if the weighted averages are perfectly equal,
Then you can choose whatever. There's no like rule to do that. Any question? Okay, great. So that's about how do we handle the missing features in practice. This is actually very useful. You will see that if you do some practical research, you'll see a lot of missing feature values. It's really annoying. And third topic, how can we handle non-binary features? So far, all the examples we have seen that if the feature can take multiple values, I just split the data set according to distinct values, right? See, for the all-look feature, I have 3 possible values. So if I choose all-look to split data set, I'm gonna have 3 branches, right? But there brings a problem, right? If my all-look feature can take 1,000 values, if I happen to choose all-look to split data set, I'm gonna add 1,000 branches. This is too large. You suddenly increase the size of tree dramatically. Right? So is there a way to reduce the tree size? That's my question. Can anyone come up a strategy to avoid expanding tree in that way? Mm-hmm.
So that if we have non-Boolean features, we just try and divide it up into ranges that represent our different categories.
Yes.
Right?
Yes. Exactly. Right. That's a smart strategy. So any other supplement? Okay.
you could turn it into a bunch of different binary features.
Yes. Yes. Exactly. Right. That's the only 2 answers I have. Do you have any more answers? I'd love to hear. But usually these 2 strategies are sufficient, right? So the first strategy is that, okay, now that I have several distinct feature values, right? So now, why not I just turn this categorical feature into several binary features, right? So we know that all can be sunny, can be overcast, can be rain. Then I can turn all into 3 binary features, whether the outlook is sunny or not, whether the outlook is overcast or not, or whether the outlook is rain or not, right? And then just throughout, I just remove outlook feature. I just leave the 3 binary features. So now that we have all these 3 binary features, whichever feature you choose to split data, you only have 2 branches, right? You'll never have like 3 branches together. So this is the first strategy. So the second strategy is that if I have too many distinct values for a categorical feature, even if I convert each distinct value into a binary feature, you have too many actual features, right? If I have like 1,000 possible values to take, and then you get rid of these categorical features, but you have to add 1,000 more binary features, right? So I want to further reduce the number of features, right? Because you have to compute 1,000 information gains to select which binary feature you're going to use to split data set. Right? I want to further reduce the computation. How can we do that? We can further group the values into disjoint sets, right? So I can first group the distinct categoricals into like 10 groups, right? Say whether your categorical features is between 0 and 100, and whether it's between 100 and 101, 200, whether it's between 200 and 300, right? So now you first turn it into like 10 categorical features, and then convert it into 10 binary features. Any question? Okay, so this is a talk about like categorical features, right? So, and for numerical features, how can we do that? So actually, we have mentioned this strategy before. We can now directly use numerical features to construct tree, right? Because numerical features can take a infinite number of values. You can now add infinite number of branches in your tree. Like how can we do that? We can use thresholds or discretize the numerical features into several regions, right? When you use threshold, then you convert numerical trees to binary features. Right? It's less than, for example, my height is less than 1 meter, is bigger than 1 meter, right? Or my height is in 3 regions, right? So those are commonly used strategies to pre-process those features.
So if you have like one column and its names or something, and you have like 10 unique names, you separate it into 10 new columns, like is the name Joe, is the name Eric.
Yeah.
But every single row is only going to have a 1, is only going to have like a 1, binary 1 in one of those columns. They're actually going to be 0.
Yes.
So if you have a lot of different like values that your original column can take, aren't you just going to get tons of zeros in your
Yes.
data?
Yes, your feature representation will be very, very sparse. It's a common used. That's actually if you do some kind of applications in click-through prediction in online advertising, you see that's always researchers, engineers are dealing with those features. So in online advertising, you have a lot of categorical features, like what's the brand of this product, what's the ID of user, and those categorical, the cardinality of those features is very, very large. So people usually first turn them into binary features. That means, okay, whether an example, a training example, which is click or not click specific advertisement will contain like 1 million features or 2 million features. It's very common. Another question? Okay, so now let us talk about a very important concept, overfitting. Right? So we're going to introduce what is overfitting and why overfitting can hurt the performance of your decision trees or any classifiers. Let us first look at a simple training task. Suppose our target function is a balloon function with n features. So what is balloon function? Balloon function means that, okay, your input are binary features and your output are binary, either 0 or 1. Right? So if I have n features, then that means all those n features are binary. So how many examples do I have in total in the instance space? So each feature can take binary values, right? Can take either 0 and 1. I have n features. How many possible combinations of those features? 2 to the power of n, right? So each specific combination of all n features corresponds to 1 instance, right? So in your whole instance space, there will be 2 to the power of n examples. So let us consider the case that n is simply equals to 2. So that means I will have 2 features. And we can pick up, for a specific example, suppose my target function is just to return the value of the first feature. That means, okay, y is just equal to x0. So for two features, I have in total 2 to the 2 instances in the whole instance space. So I have in total 4 examples, right? So these are the labels, right? So can I construct a decision tree to represent this function? The answer is obviously yes, right? If you do manually construction, you'll end up with this tree, very simple tree, right? So actually, we can show that for arbitrary Bloom functions with n features, you can always construct this tree to represent the whole function, meaning to represent the whole 2 to the power of n label instances. So now suppose we have all 2 to the power of n examples for training, for Bloom functions of n features, right? And what will be the error on any future example?
Zero.
Why?
Because you've seen all the possible inputs.
Yes. Exactly, right? As we mentioned, right? Decision trees are so expressive, it's powerful. Like when you use all the 2 to the power of n examples, you can still perfectly represent the whole data set, right? That means, okay, across the entire input space, I have seen all the examples and their branches labeled. So now I give you a label. I give you the test example. I can tell you I have seen them. I have seen the label. Right? My prediction must be correct. So my test error will always be 0, right? Does it make sense? Zero, because we have seen every possible input, right? So the decision tree can represent the function ID3 will build a consistently always, right? For these Bloom functions. So it looks like when I perfect fit between data, it looks good, right? It gives me a very accurate prediction on the test examples. But this is just the ideal case. Because in practice, there are always some noises that can corrupt both training and test examples. And when your training examples are corrupted by those noises, and when you train your tree to perfectly fit your training examples, in the meantime, it will perfectly fit those noises, right? And those noises can mislead the construction of trees. As a consequence, when you test your tree on some future test examples, the performance can drop. That's why in practice, we actually do not like the fit. So to see a concrete example, let us assume we have some noisy training set. We still are powerful, right? We still are able to collect all 2 to the power of n samples. But the outputs for both training and test sets are randomly corrupted. That means, okay, any label in the test set or in the training set has some chance to be flipped, right? Like the ground truth is false, but it's corrupted to be like truth, right? Or ground truth is truth and it is flipped to false. And both training set and test examples might have corrupted labels, but those noises can be different. So now, if I use these corrupted training examples to train a decision tree, what will be the prediction performance on the test data set? Will the test error still be 0? Why?
Because it's seen all the outcomes, but some of them are correct. It's presented with the same input. send it back to an incorrect output.
Yes, exactly right. Because now the test labels are flipped, are random flipped, right? So it random flipped, and the consequence is that the test labels are now inconsistent with the training labels, even for the same input. That means, okay, if you perfectly fit the training example, then when that training example, the input serves as a test example, your prediction is wrong because test labels change as well. We can conduct experiments, right? So suppose my chance to correct the output for both training and test has a probability 0.25, right? You have a one-fourth chance to flip your training label and test label. So these are the results, right? So the x-axis represents the number of features I used for the experiments, and the y-axis represents the test accuracy. And those standard error bars just means that, okay, I repeat these experiments many times, right? And then calculate standard deviation of the test error. So you can see, as we increase the number of features, right, the standard error bars is smaller and smaller. That means, okay, the test accuracy becomes more and more stable, right? Looks like they converge to some specific value. That specific value is approximately 0.375. So obviously, test error is quite large, right? It's far from 0. So actually, we can show this 0.375. It's just a mathematical problem, a statistical course problem. Right? We can try to analyze it. Right? So let us compute the chance that you make a correct prediction. Right? So when will you make a correct prediction? Two cases. I mean, for an actual example, right? When can we make a correct prediction? We have two cases. First case, when this particular example serves as training example, the label is not corrected. At the same time, when it is served as test example, the label is also uncorrected. Then your prediction must be correct, because it perfectly fits the training examples, and the training label is the same as test label, right? So you're gonna give a correct prediction. This is the first case. And the chance that you meet the first case is 0.75 multiplied with 0.75, because the chance that the training example is uncorrected is 0.75, right? Once subtracted 0.25, and the same chance for the test example is not corrected, right? And the correction for different types of examples are independent. Another case is that both the test and the training labels are flipped. When your training example is corrected and the test example is corrected, that means your training label and test label are still the same. Then during the training, you perfectly fit the training example. When you use that for prediction, you actually recover the same label, right? So what's the chance for that case, right? 0.25 multiplying 0.25, right? So now the total chance that you make a correct prediction for an actual example is just to just add up these two probabilities. That is 0.625, and the test error will be 1 subtracted by this 0.625, which is 0.375, right? And of course, you can consider the cases that you can enumerate all the cases that you make incorrect prediction and sum over the probabilities of each case. You end up with 0.375 directly. So what can we observe from this toy example? So first, what about the training accuracy? No matter you have noises or not noises, right? What about training accuracy? If I use the training set to construct a tree and use the same training set and predict each training example in the training set, what is the prediction accuracy? I heard that. 100, right? Because if it perfectly fits the training data, right? Every training example, it can recover the labels. So this is very natural. You can consider when does the tree stop growing, right? When all the test examples, when all the subset of examples have the unique label, right? That means it can perfectly predict every label of the training examples. Right? So the training accuracy is always 100%. No matter you have noises in your data or you don't have noises in your data. Of course, if you don't have noises in both training and test data, your test accuracy will be 100% as well, right? But in practice, as we emphasized, you always have some kind of noises in data. Then the test accuracy drops significantly, right? From our previous case, we see that the test error now becomes 0.375. This is a huge gap. What's the reason? Yeah, overfit, right? Because you fit the training data so well. The noises, even the noises in your training data, you also fit them perfectly. Right? Those noises can guide your trees toward incorrect prediction for those test examples. That's the problem of overfitting. So in practice, we always dislike overfitting because we cannot assume your training data is perfect. It is always contaminated by some noises. Right? If you fit the data set too well, your machine learner, your classifier, predictor will be misled by those noises. And the consequence is that the generalization performance is really bad.
Why is it that so I'd say 3 is less overfitting than 15, but it seems like it has lower accuracy, so how does that?
You miss one?
15 numbers of features versus 3 numbers of features, it seems like the accuracy on 3 numbers of features is a lot lower.
You mean here?
Yeah.
Oh, this is just statistical difference, right? So because every time I just randomly corrupt the examples and then do the test, right? And then you have varying performance. And when you only have 3 features, you only test on 2 to the 3 examples, only 8 examples. This is not stable. But you have 15 features. Imagine 2 to the power of 15 examples. It's very large, right? This is quite stable. Any other question? So everyone is comfortable with this concept, right? So overfitting is actually harmful when your training data have noises. Although ideally it will be good, right? But in practice you cannot avoid noises, you cannot avoid corruptions. And if you overfit the training set, you overfit the noises within the training set, and those noises will misguide your machine learning algorithm. So in summary, right, overfitting can cause your learning algorithm to face noises in data, like irrelevant attributes or noisy examples, which can influence your choice of your hypothesis function, namely the final predictor you choose. And those influences are usually bad, and usually very, very bad. So it can lead to, therefore they will lead to poor performance on future examples. So if you use neural networks, especially deep neural nets to train machine learning classifiers or whatever, there are a lot of tricks to regularize your classifier to avoid overfitting, like dropout, early stopping, all kind of stuffs. They're all trying to prevent your classifier to have like 100% accuracy on the training. So this is the typical behavior of decision trees. If you allow our decision tree to grow arbitrarily large, we can see that it can overfit the training data, right? So then how does the test performance on the future examples vary, right? So the x-axis represents size of tree in terms of number of nodes in the tree, and the y-axis represents accuracy, like training accuracy or test accuracy. So this solid lines represent the training accuracy, meaning that you use training data to you predict the training data and calculate accuracy, and then these dashed lines represent the test accuracy with some unseen future test examples. As we can see, at the beginning when we increase the tree size, both accuracy increases, right? But later, soon, we can find that, okay, when your tree grows larger and larger, your training accuracy continues to improve, right? That means that you fit the data better and better. But at the same time, your test accuracy, which indicates your generalization performance, begins to drop. It becomes worse and worse. That means, okay, there must be some noises in the training data, which mislead the tree construction and leads to poor performance in a test procedure. Right? So as we mentioned, if you do not restrict the construction, the growth of a tree, you end up with overfitting the training data. Right? Then how can we prevent or inhibit overfitting?
Ignoring some noisy gate.
Yeah, that sounds good because once you throw out those, once you can identify those noisy data, throw them out, you just kick out the contamination sources, right? But the issue is that in practice, it's very hard to know which examples are corrupted or not. So we need to use a less smarter method.
Every time we add a node, test the decision tree with the test example, and if the accuracy goes down, stop the growing the decision tree.
Yes, that's one very common use strategy.
Is it possible also to, as you add more training data, to start testing the training data before you add and see if there's huge error?
Mm-hmm. Yeah. So basically,
and maybe throw out pieces, have a threshold that throws out.
Yes. Basically, I think you two have kind of similar ideas. So, any other supplement?
Just many different splits of the data between test and training.
Oh yeah, that's a third strategy that relates to like one first. We'll discuss it later. Other ideas? So, I mean, your strategy is essentially to control the structure of trees, right? I do not want my tree to expand to be very, very large. I want to stop when it's perfect, right? So the first strategy is to just fix depth of tree. That's the most naive way to do that. Suppose my tree can grow up to like 10 levels. I do not want the tree to be that large. I just said, okay, the tree cannot grow over 3 levels. Then it stops, right? It stops, and then it just returns the majority label on each node, each leaf. That's the first. That's the first strategy, right? So there is a extreme case for this kind of controlling is called decision stop. That means I fix the depth to be just 1. So that really is the idea. Like I just split. So if you use level 1 decision tree, that means okay, you only do the data split for once, right? Now the way is that the method is that I'm gonna split the data many times. I have many simple shallow decision trees, and then I'm going to combine them together. It's called ensemble learning. And the second approach, as you two just mentioned, right? I'm going to use a held out data set. Whenever I grow my tree, I will test after the growth, what is the performance on this held out data set? And before the growth performance data set. If after the tree grows, the performance increases, okay, I can safely add these nodes and add more branches. Otherwise, I stop growing at this node. And third way is kind of post-pruning. Like, you can just grow your tree to be as large as possible, and then I'm gonna prune the branches to improve the performance. Like, I also have a held out data set, I'm trying to prune it. Here's the way, either from bottom up or top to the bottom, and by cutting some kind of branches, I will see whether my performance on the held out data set can increase or not, right? So, those are commonly used ways to control the tree growth. From restricting the tree size, I innovate the possibility to overfit the training set and increase the generalization performance. So now I have discussed everything about decision trees. I think you should be ready to implement your own decision trees with ID3 and the variance of ID3. Okay? So very brief summary. Decision trees are very popular machine learning tool, very classical but very widely used. The prediction is easy and very expressive. And the construction of decision tree is based on a greedy heuristic. The goal is to construct the tree to be as small as possible. So we implement ID3 algorithm, which uses information gain, but again, we can use any other gains like Genie Index gain or majority error to predict a tree. And it can be used for regression too. You can think of like what kind of strategies can you use to rank the trees for regression data set. And finally, decision trees are prone to overfitting unless you take care about it. Okay, see you on Thursday.
Thank you.